Hello everyone, I am glad to introduce our work, Explicit Visual Prompting, a unified approach for low-level structure segmentation. This is a joint work of University of Macau and Tencent AI Lab. In this work, we consider the generic problem of detecting low-level structures in images, which includes segmenting the manipulated parts, identifying out-of-focus pixels, separating shadow regions, and detecting concealed objects. At present, these tasks are typically addressed by domain-specific solutions, which are designed carefully as unique network architectures to learn task-related characteristics. Furthermore, the above tasks have the same input/output format and the same purpose that segments the low-level structures, resulting in similar encoder-decoder models. Hence, the designed model for segmenting specific targets can also be applied to others. Nevertheless, there is no unified framework to solve these similar problems yet. Here, we show that a unified approach performs well across all of them. We take inspiration from the widely used pre-training and then prompt tuning protocols in NLP and propose a new visual prompting model, named Explicit Visual Prompting, EVP. As the foundation model has already been trained on a large-scale dataset, the learned ability of scene understanding can lead to better model generalization on the downstream tasks. Our key insight is to enforce the tunable parameters focusing on the explicit visual content from each individual image. Specifically, we consider two kinds of features for our task. The first is the features from the frozen patch embedding, which is critical since we need to shift the distribution of the original model. Another is high-frequency components of the input image since the pre-trained model is learned to be invariant to these features via data augmentation. As shown in the figure, we take a model pre-trained on a large-scale dataset and freeze its parameters. Then, to adapt to each task, we tune the embedded features and learn an extra patch embedding layer for high-frequency components of each individual image. As illustrated in the figure above, EVP composes of three basic modules: patch embedding tune, high-frequency components tune as well as adapter. Patch embedding tune aims at tuning pre-trained patch embedding. We freeze the original patch embedding layer and add a tunable linear layer to tune the original embedding. For high-frequency components tune, we first apply fast Fourier transform to the input image and a fixed mask to the spectrum to extract the high-frequency components. Then we learn extra patch embedding layer to tune the high-frequency components. The goal of adapter is to efficiently and effectively perform adaptation in all the layers by considering features from the image embeddings and high-frequency components. Finally, the output promptings are attached to each transformer layer. We evaluate our model on a variety of datasets for four tasks: forgery detection, shadow detection, defocus blur detection, and camouflaged object detection. EVP performs well when compared with task-specific methods, which achieves the best performance in 5 datasets across 4 different tasks. However, compared with other well-designed domain-specific methods, EVP only introduces a small number of tunable parameters with the frozen backbone and obtains good performance. We evaluate our method with full fine-tuning and only tuning the decoder, which are the widely used strategies for downstreaming task adaptation. And similar methods from image classification, i.e., VPT and adapt former. It can be seen from table above that when only tuning the decoder, the performance drops largely. Compared with similar methods, introducing extra learnable tokens or MLPs in transformer block also benefits the performance. EVP achieves much better performance with similar parameters as other methods. With more parameters, the performance can be further improved. To sum up, we present explicit visual prompting to unify the solutions of low-level structure segmentations. We mainly focus on two kinds of features: the frozen features from patch embedding and the high-frequency components from the original image. Equipped with our method, we find that a frozen vision transformer backbone from the ImageNet with limited tunable parameters can achieve similar performance as the full-tuned network structures, also the state-of-the-art performance compared with the other task-specific methods. The results provide strong pieces of evidence of its potential to address a broad range of problems. We believe our simple but effective framework will be widely used in various foreground segmentation tasks, and play an important role in developing unified frameworks for other computer vision tasks.